Thank you. I'll be talking about so open quantum field theories, and we have found this very weird non-local divergences in the one-loop correction to the coupling constants. So I'll also talk about the holographic derivation of this open quantum field theory actions using recently proposed holographic Schwinger-Keldysh contour. So first of all, I'll explain why. So what do we mean by open quantum field theories? So consider a system which is interacting with a bath of environment fields, and if we integrate out the bath degrees of freedom, then we'll effectively get an effective field theory, which we call open field theory. So this can be not in equilibrium in general. Okay. So the broader question is to understand decoherence and dissipation in quantum field theories. And a final question is, first of all, to construct a consistent open quantum field theories, and to check a few consistencies, for example, whether it is renormalizable or not, or there are other properties, for example, fluctuation dissipation relations at finite temperature, and also to test other properties such as high frequency mode properties, for example, shear viscosity or bulk viscosity, those kind of things in the holographic context. Okay, so here I have put an S here because recently we have found another fluctuation dissipation relation at the non-linear level. So I'll also discuss this. Okay. So first of all, I'll describe what do we mean by Schwinger-Keldysh prescription, and then I'll go to a specific system, so 5-4 theory, and study that open 5-4 theory, open version of that. So first of all, okay, actually I'm not seeing. Okay. First of all, let's start with a system psi at a time t1, and let us ask this question: what is the amplitude of this state in psi n at some other time t2, and this is the amplitude, and where this k is the Feynman path integral, and what is the transition probability? That is just mod of this amplitudes squared, and which is this, and here rho is the initial density matrix, and this rho n is the final density matrix at time t2, and this is at time t1, and this k star is the effective kernel to get this probability. Okay. Yeah. Now if we sum over this sum over n, sum over the out states, then we should get 1, and that is transmitted in this to the right hand side by introducing a delta function. Delta function that means the degrees of freedom at the final time are identified. That's how this summing over the out states is implied on the right hand side. Okay. So right, and now
sorry, the previous
yes.
equation you didn't have this delta function.
No, because I didn't sum over the final states. So if you sum over the final states, then it will be 1, and here there will be a delta function. Okay. And in shorthand notation, it is written as there is this initial density matrix, and at final time there is this identification by the delta function, and this is the weight for the time evolution. This is the kernel, and so this we call as path integral without any source. So that is exactly 1. So here we see there is an advantage over the Feynman prescription, is that the path integral is exactly 1 in the absence of any source. So that means there is no vacuum bubbles or anything. So we don't have to worry about vacuum bubbles or, yeah, so there is no normalization.
Let me try to understand the sum over n.
Yes.
So that rho n x1, x2, I mean that density matrix was supposed
Yes.
to be a pure state.
Oh,
density
here.
matrix, there or what? In the previous page, you made a transition from
Right.
the notation
So,
of the pure state thing to a general looking mixed state.
right. So,
So now let me understand the complete set of states. You are making you're doing a sum over n.
yes.
So am I supposed to think of a complete set of density matrices or a complete set of states?
Here I have done this analysis only for pure state, but we can generalize to mixed state as well.
So for mixed state, what is this notion of complete set of mixed states? I don't know.
Complete set of mixed states.
For pure states,
right.
I understand your sum over n.
Yes.
That's there on the next page.
Mhm.
So that's what you mean.
Yes.
Yeah.
That's what I mean. Yeah.
Rho n is just n.
Yeah. Rho n is just
And then he sums over n.
Yeah. Right. Yes. Right.
So the rho x1 x thing, you allow that to be a mixed state, but rho n star is a
pure state.
Is a pure state.
Yes. Right.
It's the
Something
density
about that.
matrix of a pure state.
Is a,
Right.
Is a pure state density.
Right.
Okay.
Yes. Right. Now we'll interpret this path integral in a contour. So here I have written the path integral with in absence of any source, and here this xr is the right moving degrees of freedom, and that that is evolved by this kernel e to the power I times s, and with this measure dxr, and at the final time, that is at t equals to infinity, these two are identified by this, and then it is moving backward in time, which is by this e to the power minus is, and finally we are taking a trace here at the initial time.
This rho I is time.
Rho I, sorry, time.
It's time, right? Rho I is time or is it? So in the
Oh,
integral
okay.
also we
No,
have
that's. I'm sorry. It should be just rho I. It's not t equals to. It's just rho I. Yes.
I think you meant t equal to 0.
Yeah, t equals to 0 or minus infinity.
0 has been completely
Right. Yeah. Now we can introduce sources here.
So when you write rho I as a bound in the integral, you are thinking of this in the position space basis.
No, this is just for a particle, right, in the position. Yes. Right. So if we introduce sources for this right moving degrees of freedom and left moving degrees of freedom, and these are JR and JL, these are sources, then then this path integral is no longer 0, but this is a function of JR and JL. And we can compute Schwinger-Keldysh correlators by taking functional derivative with respect to JR and JL. Yeah. So which looks like this. And here e to the power I minus I hi is the Hamiltonian in the interaction picture. And this is contour ordered. This integral over the contour ordered. Yeah. So here this is the contour. So we should insert the operators which would follow this contour. The ordering, the time ordering should follow this contour.
These are just polynomials in X.
Polynomial in X, which one?
What are OIs?
Yeah, right.
Or you allow for arbitrary, sources for this?
Arbitrary sources, yes. I mean this operator, the operator ordering should be this way, this. So it should follow either this or this.
So the various O's, they are they're inserted at different times.
At different times. Yes.
So in the last expression, your O1, On are Heisenberg operators or Schrödinger operators, or what are they?
These are These are Heisenberg operators.
These are Heisenberg operators.
Yes.
And you're using interaction picture.
Yeah, right. So this is in Heisenberg picture and this is in interaction
So
picture.
I would have thought that. Okay, I see.
So here these operators are inserted in this way, and at some time we are taking trace. Here rho I is inserted here, and we are taking trace at this time. Oh, so it could be the other way as well. So the out of time ordered correlates are also allowed here. Yeah, is this all right? Okay, so let me now compute.
So these two contours I should think of as being separated with some imaginary time? Or
Yeah, but infinitesimal imaginary time.
which one? So, and also these lines are to be sloped like this, slightly,
No, okay, no, we are not considering anything like
because of the epsilon.
that. Yeah, so this is I epsilon, minus I epsilon, that is below this t equals to infinity. Yeah, but that's infinitesimal.
Just to fix the order, I think.
Yes.
You want to think of them as operators they first are acting first, right?
Oh, you mean
Is it control,
there could be ambiguity unless you give some slope in the ordering?
But okay, when you say contour order, I guess you are taking this as slight slope.
Yeah, he's working in terms of I epsilon,
Yeah.
basically saying. I see this interaction picture business is confusing me. Why can't you just think of this as every operator being Heisenberg picture operator?
Yeah, right. So here to do calculations in an interacting theory, then it is useful.
No, but that exponential seems to be some extra stuff which should not be there.
Which one?
The e to the power minus blah blah. If all the O's are in the Heisenberg picture, then you have got enough evolution operators anyway. That's there in the left hand side. So why do you need that? Are your O's really in the Heisenberg picture, or they are also in some interaction?
No, this left side is in
The
Heisenberg
left side
picture.
I understand. That's
Oh, right side is interaction picture operators.
the operators are interaction picture.
Yeah.
So do you do you have some separation of the Hamiltonian into some free part and the perturbation thing?
Right,
That
yes.
kind of thing?
Yes.
But I still don't know, what does interaction picture operators mean? It means evolved by H naught,
Evolved by H naught, yes.
and then that e to the power I H, why isn't it in between?
Why it is in between?
It should be in between the various operators, right?
Oh.
Unless he means, is there some overall contour ordering sitting outside of everything?
Right.
And
I should have written that.
That's what you mean.
Yeah, right. So there is overall ordering.
Okay, then all these evolution
Yeah, right.
can be clubbed together.
Right.
There should be a contour ordering symbol
Outside this
outside
trace,
of all the operators.
all
that
of
are
the-
inside trace.
right. There is overall ordering.
So this HI part should be thought of as in between, right?
Yeah.
Notation.
Right. Yes. Yeah, right. Otherwise, I would have to mention which one is in the left contour, which one is in the right contour.
Right.
And between which operators?
Right. Yes. Okay. So I'll go to specific examples in scalar field theory in 4 dimension, and I'll compute the Green's function, the propagators first. Then, so how would we? Then I'll do perturbation theory to compute 5-4. So one loop correction to 5-4 theory. So this is the Schwinger-Keldysh action, which I didn't mention maybe. Yeah. The Schwinger-Keldysh action is this, which is S of xr minus S of xl. That is the Schwinger-Keldysh action. So here I have mentioned it here. And in scalar field theory, free field theory, this is the Schwinger-Keldysh action. and the boundary condition is that that phi r equals to phi l at t equals to infinity. So this is the boundary condition which we impose at the final time. So if we impose this boundary condition, then we can compute the the propagators. So there can be 4 propagators on the Schwinger-Keldysh contour. So these are the 4 operator insertions. Right. So here both of the operators are on the right branch. So this will give the Feynman propagator, and both of these operators are in the lower branch. So this will give the anti-time ordered 2-point function, and these two are the Whiteman propagators, because there is no ordering here. So this operator can move without affecting the other. So there is no ordering. So these two are Whiteman propagators.
There's no time. That is always before that.
Right. Yes. There is no ordering.
These are Whiteman correlators in ordinary field theory.
Right. Yes. So far, I have not talked anything about open field theory. Just usual field theory in Schwinger-Keldysh language.
If there is divergence, then this comes to the same point.
Yes, there will be divergence.
In the theory you have written down, these insertion threads which are on 2 different contours won't contribute anything. I mean, why would there be a correlation between a phi and phi r?
It's because those are not exactly independent, but are related at the boundary. So not exactly independent.
And you might think that the boundary is infinitely far away, so why does it matter? But that's a fake, because you can pull the boundary in very.
Exactly.
But wait, there would be
Yeah.
a correlation coming from the boundary at the initial time.
At the initial time, yes.
Right. It's not so much that which gives you, it's that the initial correlations propagate and that gives you the whatever RL correlator in time. If you have an initial correlation between
Yeah.
phi r and phi l at t equal to 0, that correlation will propagate using
Right. Yeah.
something or other.
Huh.
So I think it's more the initial correlation propagating rather than forcing something at t tends to infinity.
But in general, not in general, sorry, say in vacuum, say, okay, we can assume that these are not, I think these two are similar statement.
No. One
they're
is
not-
about what was happening initially, and one
Yeah.
is about just the fact that there is an identification structure at the end,
Hmm.
right? So I would think that the initial correlations are propagating and giving you this gives me a better way of thinking about this. And that then takes out Shiraz's question about whether things that infinitely far away can start influencing correlators and so on and so forth.
I actually don't know how these two are related, because
I mean, you had a rho I, right?
yeah.
At the initial time. If it's thermal, you have a thermal cycle,
Mhm.
circle or something like that,
Mhm.
right?
Hmm.
That could immediately give you a phi r, phi l correlator at initial times.
I understand. Actually, these two are separate constraints, and say in finite temperature, you can impose both and compute the correlators
Without
quite
imposing
easily.
something at the initial, you cannot put the trace.
Hmm.
The moment you try to put the trace, it can be one, that initial
Yeah.
correlation, if you just put it trace.
Hmm.
But there has to be something which is phi plus phi minus or phi r, phi l correlator. Just
Hmm.
because at least then you have to construct that trace and then connect this.
In fact, to compute the correlators, this 2-point correlators, we will use this initial time correlation. Yeah.
I think that's probably a better explanation of why
Ah.
plus and minus is correlated at later
Oh.
times than forcing a boundary condition at infinity.
I mean, it's both, right? I mean,
That's what I'm saying. It's
I-
both actually.
The delta function will surely do that also.
Yeah.
But I'm just saying, otherwise you can ask Shiraz's question. I take at something at t and t prime. I said the boundary to be far apart. How does that boundary start influencing this point?
It does not matter. It only depends on your final insertion, because these are unitary evolution, so you can truncate it here only. So it does not matter actually.
When you say correlation or this propagator sensor, are you computing them with a vacuum?
Vacuum. So
both vacuum density matrix.
vacuum transmitters.
And let's say there is some operator inserted in that tip also, near the tip, so that you cannot pull it,
Yeah.
bring back. Then would there be divergence when two operators come close? Does it see
Sorry.
that that's the same time as that time?
Sorry, can you repeat the question?
So let's look at the third figure.
Yeah, okay.
And let's insert an operator O in the tip,
Okay.
so that I cannot pull this contour to the back.
Hmm.
And now let's take that first operator and move it towards that second operator.
Mhm.
Is there a divergence?
Yeah, there will be divergence. So you are inserting a third operator. Third operator here. Here.
Yeah, just so that I cannot pull it. So let just that be there.
Right. It.
And now take that operator, the first operator, and move it close to the second operator.
Yeah. Then there will be divergence. So these are usual quantificative divergences. Two operators.
But why does it see that? I don't quite see why it's because it's a different contour.
It's a no. That is then 3 point function.
Outside perturbation theory, I think he's asking. In perturbation theory, let's say you do it outside non-perturbatively, would that be right? Abhijit saying it's just a different. How does it know that it was at the same point?
Oh.
There's another operator sitting between you. Actually, in non-perturbative, I'm not sure that. Basically, you are asking there's a 3-point correlator, one of them in the between. If I take two of the indices close by,
Two of them close by meaning, but on a different contour.
on a different contour,
Yeah,
then
would it know
would it know?
that they are close? Yeah.
Yeah, you can't use the OP for this
Yeah, I cannot do the
because they're separated by.
Now they are genuinely far apart.
Yeah.
Yeah.
perturbation research as well.
I was thinking perturbation theory because the propagator between them is divergent. So that will just keep showing up in perturbation theory. Yeah.
Okay. Right. So if we impose those boundary conditions, then we get these propagators. These are usual time ordered correlator. This is anti-time ordered correlator, and these two are Whiteman correlators. And then so for a shorthand notation, we use this R for the time ordered, L for the anti-time ordered, and P and M for the Whiteman correlators. And there is a relation among these four, which is this
P and M is what please? Up and down, down and up. That kind of
plus minus
plus
theta,
minus,
yeah,
plus minus
theta,
is-
because there is a plus sign in
Plus
step
minus is
function.
linear combination up and down or?
Uh,
Oh no, it's right. Right. Thank you.
Is it a new notation you guys are introducing? Because these things are usually called G greater and G less in all of
G greater and G less, yeah.
standard non-equilibrium physics.
Yeah.
Right?
Yeah, we introduced this because so we'll be computing.
Out of time and
No, we'll be computing say bubble diagrams, triangle box. So there, these are useful. Okay, and diagrammatically we write this way that this is the usual Feynman as the anti-time ordered, and these two are the Whiteman correlators or Whiteman propagators. Now, if we include 5-4 interaction terms, then these will be the interaction vertices. So all solid lines, all dotted lines. There won't be any mixing, like two solid, two dotted. So those kind of mixing are not allowed in closed 5-4 theory in Schwinger-Keldysh language. So there is no mixing term.
There's overall minus sign between these two vertices.
There is overall minus in it. Yes. I have not written the Feynman rules here. Right. Now, how do we apply to open systems? So for closed system, this was the Schwinger-Keldysh action.
Why isn't diagram the dotted one and this thing?
Yeah.
Why is
It's because this dotted and solid are mixed only at the boundary. So by these two propagators, and the interaction terms are inserted either on the right contour or on the left contour. So that's why there won't be any cross coupling.
But phi r always is a solid one?
Phi r is always solid one, yes. But this is just a convention.
But in one loop, you in loop corrections, you generate effective vertices.
Yeah, right.
No, even in a closed
No,
system.
but
Right.
basically is a solid one and then.
Because it's because
The thing
since-
that propagator that contracts with the pi r to the 4 vertex is always the solid thing.
right, yes, because the action is del mu phi r squared plus
Oh, sorry, yeah, the r was the
Yeah.
top.
Yeah.
R was the top.
yeah, so it's like this.
Oh, I see, okay, fine.
So this is the action. That's
So effectively, these are your control labels, R and L.
yeah. Okay. So this is the action for a closed system, and now so the claim is if we I want to construct action for open systems, then we would just add mixing terms. So there was no mixing term between phi r and phi l other than at the boundary. So here we just add a mixing term which would mix the left moving and right moving degrees of freedom. And this SIF is called the influence phase, Feynman-Vernal influence phase.
But SIF does not change your SIF cannot have a term which is only function of phi r.
Yeah, it can have rights, but those are imaginary. So here this Schwinger-Keldysh action is completely real, but this influence phase can have imaginary part. So it can have all phi r, all phi l, but those are imaginary.
So they have to be careful, right?
Right, yes. I'll come to that, I'll explain.
So you're not considering coupling the R guys to some bath, R bath, and the L fellows to some L baths. You're not doing that.
No, I'm just looking at effective field theory.
So
We don't know how to derive
you're
this.
representing open system by a coupling between R and L. What's the picture of that?
I'll give one example.
Can't
Clear.
you not do it for a path, like take the basic without the phi 4 interaction?
Mhm.
It's a quadratic theory. You can couple it to a quadratic path and exactly get what the SIFs are. And
Yes.
then add interaction to it that will keep modifying and generating terms.
True.
Why
But
is that not
problem is in field theory, it's not very easy to derive from a microscopic theory. That is one point. In interacting theory, yeah,
You first do the
linear.
connection for the linear theory and then add the interaction.
Yeah, you can do that. Certainly, you can do that.
That would
Yeah.
be more well defined rather than trying to predict this should be the form of the because you have actually a concrete calculation there.
Yeah, we were trying to derive from a microscopic theory in an interacting
No,
system.
just make your bath non-interacting.
Yeah.
That's what you are going to integrate out, right?
Ha.
So as long as that integration can be done exactly, which means the bath has to be a quadratic theory, you should be able to get what are the terms.
We are trying to derive with this kind of theory. Say chi is bath and phi is the system. Then we tried with a nonlinear theory. Actually. We tried with this kind of system bath coupling.
But if you just try with a linear system
linear.
of coupling, you can get an exact answer.
Yes.
And then your interactions will keep generating added coupling. And I guess that's something Gautam is asking for. Can you write down?
I just wanted to understand that fire. So I presume that you have an example.
Yeah, I have one example.
And in fact, your coupling was phi chi squared plus
Yes.
del chi squared plus x squared chi squared, right?
Right. Yeah.
So that's basically what Rajiv was talking
Yeah,
about.
that will also work.
Because it's free in chi.
Yes.
Free time, so I can be integrated.
Yeah. So that's easy, right?
So there is some assumption about the mass of that.
Assumption about the
Small compared to
Right.
phi
Yeah.
of-
Yes. The mass of this is much smaller than this.
Otherwise it will be like this.
Right. Yeah. So the problem here was we were trying to integrate out all modes of chi, and there were some higher divergences. So we really didn't know how to do this. Either some low modes of phi also need to be integrated out. That we don't know how to do that. So we couldn't actually could derive. But right now actually we're trying to derive now from.
Mass of the chi field, small mass, you do not protected it everything, because you are doing that integral exactly.
Right. Oh no.
If you put a small, I understand if chi is massless, you would get.
No, we did put a mass to chi.
Even with the mass, you get infrared.
Yes, and with this interaction term.
Sort of like Fermi C will have divergences even if the basic thing is massive. There's so many low energy fluctuations around the finite temperature state. That's right.
So, but where is the, I mean, this could be done at
Yeah, we were trying to do this at zero temperature. Yeah. Okay. Right. So one example here is this. So for example, we have a harmonic oscillator that is interacting to a thermal noise. Then if we integrate out the thermal noise,
So you've got your ion divergences even at zero temperature?
even at at zero temperature. Yeah. And that came from box diagrams. This kind of diagrams where these are phi, and these are chi. So the ion divergence came from these kind of diagrams. The other diagrams were fine.
Is that because you're trying to do perturbation theory?
Yeah.
Why not integrate out chi exactly? Many of these divergences may cancel for all you know. I mean, chi is a quadratic theory.
Yeah.
Why not just integrate out and get a theory for phi?
But you know, this for the 5 to the 4 coupling, this will be exact, right? One loop with as many phi insertions as you want will be just the exact thing. So you won't be able to cancel this against anything else because for 5 to the 4, this is the only diagram.
The stuff that you want to do will lead to the same thing. You are talking about no determinant of del square plus phi. So the expansion of that quantity up to 5/4 order is only this diagram.
You were saying about this, right? Chi is a function of phi. To keep linear in chi and. Oh, this only.
Yeah. No, that's why I said if you have a del square plus m square, small mass, that will correct it, right?
Well, the claim is it's not. But this one is exactly the expansion of.
Yeah.
No, I see that there will be a divergence if I take del square plus phi, log determinant of del square plus phi.
You're saying that how come there is an infrared?
Yeah, if there is a del square plus m square,
I don't
you
see that.
regulate all your divergence.
I don't see that.
The infrared comes from if you take this limit that m chi is much less. So if you take this limit, then the infrared.
For finite and chi.
Yes. Okay. So this is an example, and this is exact because all were just quadratic in bath and system. So here, so once we integrate out the harmonic bath, then we would get this kind of influence phases. So this is just harmonic oscillator, just harmonic oscillator.
quantum mechanics, it can be done.
Yeah.
This will be
Actually-
about 500 Bernoulli.
Right. Exactly. Right. And here this gamma is the dissipating dissipating factor, and his alpha is the strength of the noise. And you see that this is completely imaginary. So this will make the frequency to be imaginary, because this is xr squared. So this is the frequency term in the original harmonic oscillator degrees of freedom. So this is the frequency term. So this will make the frequency to be imaginary, and along the forward time contour, and along the backward time contour, that is xl squared, that would be, so that frequency will be complex conjugate to the right moving frequency. So here there is a mass term, frequency term, which is omega squared xr squared, and here omega squared xl squared. And now we have, along with it, we have I by 4 alpha, and here, along with it, we have plus I by 4 alpha. So the frequencies are complex conjugate in the two contours.
One question. If
Yeah.
you work in the usual, which is the symmetric and asymmetric basis, right?
Hmm.
That's the other basis where
Mhm.
you don't work with the time order but retarded and advanced.
Mhm.
There, the gamma term comes in a different part of the action than the noise term. The noise term will be proportional to both antisymmetric x, whatever, x quantum,
Yes, yes.
right?
Hmm.
And then it's not that you just add a frequency plus an imaginary part.
Hmm.
It just comes at a different level.
Right.
And in fact, as you know, if you do saddle points, it will come as a noise term in the
True.
right hand side.
Mhm.
So how is the noise term equivalent to this making omega square into omega square minus I over 4 alpha? Is that easy to see? So that's a claim you're making.
Yeah.
That I have a stochastic noise
Mhm.
in my theory,
Right.
and that is equivalent to just making omega square to omega square minus I over 4 alpha.
Right. So it's just making the existing parameters to be imaginary. Yeah. So what are you asking exactly?
No, because I am used to this
Okay.
noise term coming in a
Mhm.
different part of the action,
Hmm.
right? And then
Right.
the retarded propagator does not get modified just by this I over alpha. It's something else that happens.
Hmm.
Yeah.
Oh, so we adapted this language because we are used to do calculation in using Feynman correlator. Feynman propagator. Say we compare a bubble diagram or any other diagrams.
So that's
So-
just a propagator changing sign. That's that.
So yeah, even if you do this calculation in average difference, so
No,
finally,
I'm just pointing out that this is an interesting way.
okay.
It's true that something which is noisy and stochastic, you were saying is equivalent to changing omega square and adding a imaginary part.
Right. And
So you have two constants, gamma and alpha. So
yes,
gamma
is that
the dissipation,
and alpha is the strength of the noise.
alpha is
Say-
the strength of the noise.
So the classical equation was x double dot plus gamma x dot omega squared equals to alpha the noise. So this was the classical equation.
Microscopically, we have to do these gamma and alpha parameters in the bath action.
In the bath, right? Oh, this will be some. Yeah, this will be function of bath correlators, right?
No, in the bath you probably have some y, that's a y degree of freedom for the bath. Then you would have some coupling with y square x type coupling,
Right.
and also mass, some y square.
Huh.
So that's where these gamma alpha.
Right, right. So gamma is a function of temperature. I'm sorry, gamma is not a function of temperature. Gamma is function of bath correlator. So that will contain the system bath coupling, right, and masses, as in frequencies. Sorry.
That imaginary term drops out from the equation of motion of xl plus xr, right?
Last. No, why?
Suppose I compute the equation of motion varying with respect to x, or maybe I'm getting the other way around. If I compute the equation of motion varying with respect to xr, I
Okay.
get a 2xr there,
Right,
and then I'll get a minus 2xl there.
right.
Sorry, 2xr minus 2xl. So I
Yes.
suppose what I say is that if I set xl equals xr, then that does not contribute.
That doesn't contribute, right?
So the first term continues to contribute, even if I set xl equals xr.
No, this is again zero, right? It's
No,
again
I-
zero.
I'm-
So xl dot you also have to set equal to xl dot.
Yeah, but suppose I do that. So if I vary with respect to xr, I get xl dot.
Ha,
Then I vary the other guy with respect to xr, I still get xl dot because I have to integrate by parts.
right.
So I get 2 xl dot, and then I said xl dot equals xr dot, I get something.
Right, yes,
So that contributes to the leading order equation of motion for the sum,
yes, yes.
but that term does not. So that's just friction. You see, the sum goes with friction.
No, that's not true. I mean, it should, XL plus XR is what is, the symmetric
Actually,
combination is what would be the
right,
natural
right.
variable.
Yeah.
It must have a noise term. That's what he's trying to
So,
write.
right. So if you compute for say XR, equation of motion for XR and XL, then you have to take an average, and that will be the classical equation of motion.
So that's what Shiraz was saying. If you take XR plus XL, according to him, I over 4 alpha, that guy looks like simply XR
Yeah, it
minus
cancels.
XL whole square. So why doesn't that drop out?
Maybe I'm being wrong. I was varying with respect to XL. I'm varying with respect to XR on solutions in which XL is equal to XR. For such solutions, that does not contribute.
That does not contribute,
Whereas
yes.
the first term does contribute.
Yes.
So for such solution, I mean, there's consistent truncation in the system, right?
Right,
So
yeah.
set XL equals XR, and in that consistent truncation, you just see friction but no noise. Just classic, quantum mechanics thing. Is that right? Or?
Yeah. So why is this happening? Right. Value is XR.
Do you get decoupled equations of motion for the average and the difference?
Yes.
And that is the statement that this is the one with the average. So you don't care about the difference because you said that.
Yeah, that noise is probably the difference.
No. Noise is not exactly difference, but
Is the noise zero and difference is zero?
yeah. Right.
It's consistent with that.
Yeah. If exactly.
Which is what I was saying. It couples to the antisymmetric.
Right. If the noise is zero, then
Zero.
the difference is zero.
So
Yeah.
you know the classical saddle point is not taken by taking a variation with basically the classical saddle point, what you do is you write everything in terms of the symmetric and antisymmetric components, that we call them classical and quantum. Then you take del phi quantum or x quantum and then set x quantum to 0, and that's basically what you're left with the classical part.
Right.
Okay. So what happens here is you get a term which is square of, let's say, phi quantum or x quantum in this, because it's XL minus XR whole square. Okay. Now you do a Hubbard-Stratton. So the way to do it is you cannot just look at this action and take a saddle point. You have to do a Hubbard-Stratton of which on that term, which is XL minus XR whole square, to convert it to a linear term in XL minus XR. Okay. That will bring the 4 alpha on top, because it's 1 over 4 alpha, right? So, and then you take the derivative I'm talking about, you're left with that alpha on the side, and not multiplied by any x or anything. That's how you get the noise.
Yeah. So you have to vary with respect to XD. That will give this equation. To vary with respect to XD.
Wait, is x difference, is the equation of motion x difference homogeneous in x difference? Is every term in the equation of motion for x difference not proportional to x difference?
Yes. Because if you have a term without x difference, then I mean you have to put that to be 0. Otherwise, the trace of the microscopic theory won't be preserved.
You get the XL plus XR times XL minus XR dot, for example.
Yeah, that is allowed term.
So the equation of motion do not, if you take the saddle point for this, you will have terms which will come with the XL plus XR.
Oh, in the equation of motion. I was talking about the action.
I was trying to say, is the equation of motion every term proportional to XL?
Oh, not in the equation of motion. Sorry. In the action, every term has to be proportional to XT.
Yeah. So the equation. So then I was doing it wrong because then I'm not allowed to set x minus x.
Exactly.
X equals x.
So you have to be careful with that.
So this was an action, and yeah, as we are discussing this, that if we put phi r equals to, this will be xr equals to xl, then this influence function, this influence phase vanish for both open and closed system. So if we just put phi r equals to phi l, then for closed and open system, this action should vanish.
No, but the action seems to vanish, but as Shiraz argued, that the equation of motion coming from the first term, that does not seem to be vanishing. I mean, it's just there, and both the terms are equal up to a partial integer. Therefore, it's just twice xr
Yeah, in the equation of motion, yes.
So therefore, so you're saying action vanishes.
Action
But
vanish.
the equation of motion is finite.
Yeah, equation of motion is non-zero.
Yeah.
Yeah.
Yeah. So that should be the same thing as a consistent truncation.
No, I think he's saying that I was trying to work on the solution where xn was equal to xr, which meant x difference is equal to 0. And Rajdeep and he are saying that you cannot set x difference equal to 0 because there's a source at the x.
Yeah.
The equation of motion is x difference, what, del square x difference is equal to something.
First take a derivative with respect to x difference and then set x
Then set-
difference. X
exactly.
to 0,
Yeah,
which
yeah.
is not the same as setting x difference to 0.
Right.
and working with
Huh.
Yeah, so I don't know what to make of this last sentence.
Hmm.
Action vanishes if phi r is equal to phi l, or both open and closed systems. What do I do with this observation?
Yeah, so this, so I'll explain this again because this come from the microscopic unitarity. So I'll explain this.
I think it's the statement that you diverge.
Yeah, right.
It's more the trace row is 1.
Test row is 1. So that is the,
Phi r gives you u.
It's a check of that.
yeah, right, right.
Yeah.
Huh. Yeah.
If you generate a term which makes this non-zero, you have done something wrong.
Right. So this will break, if this is non-zero, then this will break the unitarity. Huh. Now I'll come to open phi 4 theory. So this is the closed form of the action. So I've written the closed action where there's the kinetic term, mass term, and interaction term for both phi r and phi l. Then I'll add interaction terms, which are this. Here we can have this kind of terms, the cubic r, cubic l, and this kind of mixed terms, which are phi r squared, phi l squared, phi r, phi l, all possible terms which are either quadratic or quartic. And we have also made the coupling to be imaginary. As yeah.
Sorry, I'm going to ask you just one more time.
Yes,
If
yes,
you could go back one more time.
Yeah, yeah.
Getting a little confused. I presume that if you want to get the equation of motion for phi difference, you have to vary with respect to phi sum. This is correct?
Yes.
Okay. Now, the variation of that last term with respect to phi sum is just 0,
With respect to phi sum is 0. Yes.
right? Because
Yes.
of phi difference x
Squared.
difference squared.
Yes.
Now, the variation of this term, this term can be written as what? It's phi
Okay.
difference times phi,
Let me
probably
write
phi
it.
difference times phi dot phi sum.
Let me write the full action. So the action in that basis, yeah, that's fine. It would be something like the x average, x difference dot, not sure about the sign. It will be positive minus. So gamma x a dot xd plus some coefficient, maybe 1 by 4 alpha xd squared. It's of this form. Not sure about the coefficient, but it's of this form.
E is sum.
Yeah, A is sum.
That's okay. Excellent. Now let's vary with respect to phi xa.
Xa, then it's x d double dot, and there is what?
Minus gamma xd. Right?
Yeah, minus gamma
xd dot plus
x
gamma xd.
d dot. Yeah.
Okay. So now this
Minus
equation of
gamma.
motion looks completely homogeneous to me in that x difference.
Hmm.
So it seems like I can set f difference equal x difference equal to 0 classically. Is this right?
Classically, x difference equals to 0.
I can set that equal to 0.
Hmm.
I just want to understand whether this is a consistent truncation of the equation of motion. It looks to me like from your formulas that it is. Is that wrong?
That means
Yeah, so what happens is, so this is, okay, so, okay, let me say what works, and then we can come back to why your use is wrong. So of course, I told you that, you do all this Habermas or whatever, just convert it into a linear term with some auxiliary field, right, and then take the derivative and then you get the noise. You could have said, why do I want to do that? Let me just take the original action, which is what you are doing,
Yeah.
and you would get an answer which has no impact of the noise. The noise drops out of your equation.
At least classically. I mean,
Yeah. So the point
in the Hubbard set
so the point is, here is the point. If you get a term with this imaginary coefficient, which couples to only phi d or xd, okay,
Hmm.
taking, you
Now why, I'm just saying what gives you correct prescription. In fact, we have wondered what actually would prompt us to always do this. We have seen it with different other kinds of noise. So what happens is, anytime you get a term which is even in XD, right? You first need to get the correct classical interpretation. You first need to convert it into something which is odd in XD by using auxiliary fields or something like that, and then take a classical equation of motion, and that works. That gives you the correct stochastic differential equation. Okay. Now, I'm just saying that this is large bar noise or something. There's some other things you can do more complicated. Every time this comes out to be true, but I don't have a very concrete reason why it needs to be done.
No, but even if you did that, why wouldn't I?
See, then I would have gotten some term which is alpha times some eta times XD.
Yeah.
Yeah. So this is not what I am interested in. I am more interested in what is the equation of motion for the average.
No, he wants the equation of motion
For the difference.
Oh, the equation of motion for XD will remain
Homogeneous in XD.
homogeneous.
Homogeneous in XD.
Classically, one can set it to 0. I agree. Quantum mechanically, it will fluctuate.
It will fluctuate.
Yeah.
Then to look at equation for XA, you should take del of this with respect to XD, and then you can set XD to 0 because it's a consistent solution. But
And when you do that, you get pure friction. Is this right?
yeah, but
Yeah,
if you
yeah.
had done with auxiliary fields and converted that 1/4 alpha XD square into some eta times XD, right? With some Gaussian eta square over 4 alpha square. So then basically you will see, now if I take del del XD, there is an alpha hanging out, not coupled to any fields or any X. So in my equation of motion on the right hand side, that's the noise term that he is writing, X double dot. Okay. So the claim is, whether you do this auxiliary field transformation or not, you seem to end up with difference equations. Okay. And at least what we know from thermalization, at least if you have a dissipation, you need a noise. If you did not do this auxiliary field transformation, you would not get that.
But your alpha now is an auxiliary. No.
So all I'm saying is,
Oh, I see.
you just convert it into e to the power eta XD into e to the power eta square over alpha square or something.
But having a dissipation without a noise, that is also consistent, right?
No. Well, it may be consistent, it will never lead to thermal.
It will never lead to thermalization, right? Yeah.
Clear.
So that right hand side can never vanish.
But so this is the weird thing, that it's happening because I convert the term which is completely quadratic in XD into a term which is odd in XD. Now you will later get terms, I'm sure he's going to show us, where you can get whatever XA square XD square. Okay?
Okay, I won't go to that AD language.
But whatever similar terms will come up. Again, if you do Hausser-Novich, you will convert it into an XA XD, right? That's like a mass or the frequency of the harmonic oscillator. But now this is a frequency which is noisy.
No, but if you've done any legal manipulation, a solution will map to a solution.
Yes.
So there must be a solution in which the XL is equal to XR, and then the auxiliary field does whatever it does, but this obeys pure friction.
Yeah.
Otherwise, you've not done a legal manipulation. Because if it's a solution here, can't change.
Yeah, I mean there can be many saddle points.
Right.
Correct. I mean nobody said that the saddle points have to be unique, but you can then ask which saddle point would you normally think of if a harmonic oscillator is coupled
may not
to
be
a thermal
physical.
bar. Yeah, so that's
Okay, thank you. Okay.
as a purely back argument, yes, this saddle point also exists.
Okay.
So here again, from the trace preserving of the density matrix, we can say that the coupling constants are not independent. So there will be relation between this mass, 3 mass terms, 3z, and these 3 coupling terms. These 4 coupling terms, sorry, lambda, sigma, and delta.
So
Okay.
that's from what condition?
This comes from the the trace preserving condition, that trace of the density matrix has to be 1.
Meaning that if you put phi r equal to phi n,
Exactly.
then the thing should vanish.
Should vanish, this action should vanish.
And sorry, and how did you know that? Sorry. You said SK action for theory is
Huh.
there's some form you've given. This is the most general form, or you put some constraint?
No, yeah, this is the most general form for
Just most general by dimension.
right.
With M's, not saying anything about reality or imaginary or anything like that. They're all complex numbers.
They are complex numbers. But no, sorry, this is Z delta, M delta, and these are real.
Yeah, how did you know?
This came from from this example. You can see that here these are real. So this XLXR, this is real. Sorry, this is just 2 by 4 alpha.
I understand, but roughly, I mean, how do you know that?
So here, so yeah, so if you put phi r equals to phi l, then these terms won't vanish. I'm sorry.
Everything together vanishes.
Yeah, all will vanish. I think if you put a real part, so you could put a real part. So once you put this phi r equals to phi l, then this action should vanish, and the real part, I think that will also simultaneously vanish. Otherwise, yeah, I think that is.
I think the rule
let me
is
see.
slightly easier again in the A and D language, so maybe if I can use that. Anything which basically
Right,
only consists T's will have a anti-Hermitian structure, which means if you are making it local, it must be purely imaginary.
And how do you know this?
Okay, so if you write down the basic initial field theory without any of this,
Right.
This is a structure you will see in that step, that anything that has to do with whatever initial conditions, anything which basically couples to phi quantum. And then the claim is that you should preserve this structure. Well, in effective field theory, its structure is always preserved.
Right.
And the argument that is given is that at least perturbatively, if you say that there is a propagator whose one part is anti-Hermitian, you can work out in all orders of perturbation theory that part will, you have a matrix propagator, for example. You can basically work out to all orders in perturbation theory that should remain anti-Hermitian. Okay. Now you can, at least to all orders in perturbation theory, there will be
Yeah, so
answer.
there is a proof in open system literature. It's called Lindblad equation. So this is the differential equation for the time evolution of the density matrix, and there is this there is a particular form which need to be preserved to get some Markovian limit. So we just borrowed that.
But this has nothing to do with Markovian.
No, these are local. These terms I have
Local,
added.
but I'm saying this structure is more general. I can write
Oh.
down the most general non-Markovian thing. I can write down time-dependent kernels instead of Z delta and all sorts of things. They will still preserve this anti-Hermitian structure. Okay, so this has nothing to do with getting Markovian equations out of it. If you have local things, you get Markovian. That's fine. So the structure is more general. Anything that goes with only phi quantum.
Okay.
Or
We
even
borrowed.
powers of phi quantum.
So we borrowed this structure from the Lindblad equation. That if you write the path integral form of the Lindblad equation, then you will get
What
this.
I'm telling you is you
Okay,
can do a more general argument,
Okay.
calculation, where you don't have Lindblad or don't start from local, but this structure of anti-Hermitian, there's a part which is Hermitian, there's a part which is anti-Hermitian,
Right.
and that object remains, that works through. And at least in all orders in perturbation theory, you can ask what would have happened if in a non-perturbative, I don't know. There's an argument why this should be preserved.
You're just saying start with some fields and do the integration out, and you'll see that this all.
You will see that this.
Okay.
These structures, I always find it easier to understand in the A and D language. It's kind of slightly, you have to work towards that
Okay.
from this kind of an argument.
We also did some analysis in AD. That's in our paper, but I thought people will understand more this in RL language.
See, because ultimately you want to write down a saddle point and interpret those terms.
No, we won't do that.
We won't do it.
Okay. So this is the trace preserving condition, and by imposing this trace preserving condition, you can say that the action should vanish. So the path integral should be 1, and we will get these three relations among the coupling constants. These we call Lindblad conditions.
But Lindblad doesn't say that you started from a microscopic unitary.
No,
picture.
we also didn't.
So then why should I preserve trace flows?
We are assuming that there is a microscopic theory. Even if you impose the Lindblad structure, then also you will get these conditions.
See, if you look at Kamanev's book,
Kamenev's book, yes.
it starts by giving you, or at least all out of derivation theory proof that this structure has to be there. That without assuming anything from Lindblad.
So given this action, so these are the Feynman rules. These three are the propagators, and there are 5 vertices, quartic vertices. Right. And with this, we will compute loop correction to the vertices. And so there will be tadpole and bubble diagrams, which are divergent diagrams. And we computed this loop correction to mass and the other coupling, and these are the beta functions for all of the coupling constants that were obtained from tadpole and bubble diagrams. And so there was also a consistency check that need to be checked, which is yeah.
We can just go back. So the divergent corrections to mass and the coupling,
Right.
and what sigma was what?
Sigma, right.
Okay.
Right. And we also studied the flow equations, and there was actually I forgot to write this. So there was non-trivial fixed points.
So one second, when you are deriving this, what is the propagator you are using?
Propagator for free field.
Are you using the propagator for free field?
Yes.
Without all these terms?
Yeah, without all these terms.
Why are you allowed to do that when you have quadratic corrections, which are structurally different?
We assumed that the imaginary part of mass and all of these couplings are small. So in that limit, we are doing perturbation theory.
Usually a bad approximation, because see, if I take a harmonic oscillator and a damped harmonic oscillator, long time regulations will come from the damping. You will get an exponential which will do various things, and that will change the structure and the scalings of various objects. So if trying to get a damped harmonic oscillator out of a harmonic oscillator by perturbation is usually a bad idea.
Even you should have put the imaginary parts of the mass as well.
Those things regulate your various things. In fact, you will not get many of the logs that you are getting will just become, polynomial divergences or something like that. Because see, whenever I put omega plus I gamma or something like that, that starts to regulate various parts of my integrals. See, the problem is once you have dissipation, right, the scaling of various terms changes. Right? Because we are saying something del t has come into your action. Right? Phi del t phi has come into your action. Whereas you started your power counting by saying, there is a del t square phi. This term is always relevant in that. Phi, if I start with a real where phi del t square phi is what is giving me the basic power counting, phi del t phi will always be relevant.
Will this be important for short distances, distance divergences also?
Distance, okay, so that.
I mean, I can imagine that long time behavior has completely changed by this equation.
Right.
But short distance maybe not so much.
Short distance you might have But you know, so when you are saying short distance or short times, then you have to ask whether you can do the frequency integrals like this. For that, I need to basically say I have some long time steady state that I can just go to frequency space and do the integrals. Right? Short time transient behavior. So yeah.
And the steady state around which you're doing the integral is just a vacuum. The small fluctuation. I mean, it just
See, the point is that if things are okay, the gamma will take you towards the thermal state, right? In some ways, you can say that that's an effective change in dimension of the field theory or something like that.
Actually, we are looking at high temperature limit, high energy limit. We are computing loop corrections.
Yeah, even there.
Even there,
Purely in the momentum and frequency space, he can do this. Because you have 1 plus p square plus m square plus delta m square.
yeah.
And you can make a perturbative expansion in delta m square.
That's not always a good idea, no?
No, purely in the frequency space. Then where you can take the p square to be large.
This is the same question as suppose I had a standard propagator and I had a dissipation coming, so I should have done it with the m square plus delta m square together.
Correct.
The dissipative propagator has very different scaling. What you were saying is correct. If that term in the zeroth order was not either marginal or something, perturbation theory is about the rest.
Yeah.
I'm saying even at the power counting level, this is actually a term which is going to grow with you.
Yeah, but it's going to grow in the IR. It's
Yeah.
almost, So I mean, he's looking at short distance segments.
Okay.
I mean, physically, dissipation affects things at long times.
Long times, that's fine.
Not very much at short times.
Yeah, and these imaginary terms are not actually flipping the sign of I epsilon. Actually, it's the same side. So originally it was minus epsilon, and now it's moved in this direction, not to the other side. So
Yeah, I completely agree with your statement about long time. We should see IR divergences which are presumably cured by putting
Are you getting iron divergences out of this?
some non-local divergence. So the UV and IR are mixing.
You are also getting
Okay. Right. So these are the beta functions. Right. And we also have to check whether the Lindblad conditions, the trace space having conditions. Zeros of what? Oh, right. So that was imaginary lambda plus sigma is equals to 0, and real lambda minus 2 sigma equals to 0. So if we put this, then all, is it correct? Sign is. I'm not sure about the sign, but let me see. Right, 2 plus, yeah, right. So the claim is there is a non-trivial fixed point. So if we impose this, then all of the beta functions vanish. Yeah.
And what should I make of this observation? That there is a
Yeah, we're trying to think because this coupling right, have a signature of openness of the system. So what are the behaviors of this coupling at different scales? So that might give some information about decoherence. So that was the idea. And since we have found some fixed point, so that means so the system can be can be closed without even non-zero values of say lambda and sigma. So I'm sorry. Actually, it should be look at it this way, that so around that fixed point, the system can be I'm sorry. What is The system is effectively closed at that fixed point. Yes.
Why does that mean that?
Because there all these energy.
Because, you know, for a closed 5 to 4 system, there is no fixed point, right?
There is just at 0. There is no fixed point. Yes.
Yeah. So what does this mean that there is a non-trivial fixed point? That's only came because of openness.
Yes.
And now, how should I think of the fixed point in the open system?
Yeah. So it's effectively.
Conformity at the end?
Yeah. It's effectively
So it's a
closed
different type of properties.
for some combination of the coupling.
Why is it effectively closed?
Because this coupling doesn't flow.
So why does that mean it's effectively closed?
It means it's scale invariant. But why is
Scale
it
invariant.
closed?
It's not closed. It's not closed. It's not closed. Scale invariant at those values of the coupling. Yes. Yeah. But we also have to check a consistency condition that the Lindblad condition are not violated at one loop. So the trace preserving condition is not violated at one loop. So if the beta function of this combination actually are 0.
Proportional to.
Yeah, proportional to the Lindblad condition itself. So these are not 0. Right. All right. So this analysis was done for bubble and tadpole diagrams. But to prove that this theory is renormalizable, then we also have to check whether the triangle and box diagrams converge.
One question,
Sorry.
and this is more to Sharath, actually,
Okay.
in terms of what you said. So,
Maybe wrong.
No, you were right, but I'm just saying that suppose I am starting from vacuum, adding whatever bath and etc., and things will fluctuate and so on. And then this is true for short time behavior,
Yeah.
right? But then at short time, I don't have time translation invariance. I would have to do some resummation or something like that to get it, because I'm starting from somewhere, the system has to move in time to some other steady state once you have the thing, right? So when you do this frequency momentum space things, you're assuming a steady state by definition.
Yeah.
Otherwise, so there is some discrepancy between saying I will start with a vacuum and add the bath and fluctuate and it captures short time behavior, and using Fourier transforms in saying it's all function of t minus t, right?
You're saying time translation is broken by the fact that I have an non-trivial initial state?
Any state, because I'm saying it starts from some initial state, and with the coupling to the bath, it goes to some other steady state. Well, if it remained in that state, then it's a trivial dynamics. I don't need to worry about anything, right? So by definition, at short times, the thing has broken time translation invariance.
Yeah. Right. But the rules here may be different. But typically in quantum field theory, the short distance behavior doesn't really care about the state.
Yes, but in quantum field theory, you are not really looking at time dynamics like that.
I agree, the rules might be different. But I think here they were looking just vacuum. That's like a time translation invariant state. And you could have put this here or you could have moved it back.
Yeah.
So in exactly their calculation, I don't even think they will see your issue.
Yeah, in the calculation you will not see, but I'm just
You're saying physically.
It will
Yeah,
not
it's a good point.
represent the
Yeah.
physics of what you were.
I think.
Yeah, but okay.
So you're saying if the initial density matrix has a
Whatever it
what
is.
has microscopic results or what is
Then, let's say it's a vacuum state.
okay.
You have added bath, right? So you are exchanging energy with something or other, right? So in the end, you will go to a steady state which is a different density matrix. Maybe most likely, if everything is fine, you will go to a thermal density matrix, because now you have coupled to a bath. There's some energy exchange. There is some finite energy density in equilibrium system. So the short time dynamics is
Oh, I see.
one thing going to another thing. Right? So there's no time translation. Time translation invariance will only come when you say, well, whatever had to happen has happened, and I'm in some steady state, right? And what is the description in this steady state? Right? Then you would basically write down things like that. But then I think you have to use the regulator scale, because you are now really talking about a long time limit. But anyway, so that's a more technical point. I think we should let you go on with this.
I see what you're saying.
When you compute this beta function
for
Lambda will be
lambda,
coupling,
right? So right, yeah. For example, this was this. It can be this kind of this, and there are lots of diagrams. Actually, 10 diagrams.
So not box.
Not box, just a bubble, and
Why not box?
because box are convergent.
More properties.
Yeah, 4 properties. Yeah. Right. Right. So we will also have to check whether these triangle diagrams are convergent or not. So that means the 6-point functions or 8-point functions, those functions has to be finite. So those one has to check. So now I'll discuss non-local divergences, which actually appear in this kind of diagrams, in triangle diagrams. So what do I mean by non-local divergence? Is the divergence would be of this form: some function of k divided by d minus 4 in dimensional regularization, or some log lambda in cutoff regularization with some function of k. Yeah. So this kind of divergence are called non-local divergences, where this function f of k squared is a non-local function. That means it is, for example, say 1 over k squared. Okay. In
Sorry, what do you mean among different channels?
among different channels. Okay. Say, for example, in 2-loop diagrams in 5-4 theory, so there are non-local divergences. So if you add different channel, then those divergences cancel.
And can you give just one example? What do you mean by, I'm not understanding your word channel.
Yeah, right. Say the diagram was 2-loop diagram, right? Something like this, right? For example, this diagram. This diagram is the diagram.
By channel you mean all 2-loop diagrams?
All 2-loop diagrams, not channels. All 2-loop diagrams. Yeah. Yeah, right. All right. So, but in these cases, if we add all contributions, then this kind of divergences don't cancel in open systems. So to discuss that, let me explain one example of such non-local divergences. Here we have considered only one loop diagram with only Whiteman propagators. So this is in d dimension, and there are d minus 1 Whiteman propagators. Okay, and here q is the loop momentum, and this k1, k2 till kd minus 2. These are, so here we call cut momenta, because it consists of only cut propagators. So these Whiteman propagators we also call cut propagators. So this is the integral expression of this loop in d dimension. So it seems that the superficial degree of divergence of this integral is d, come from this measure, and there are d minus 1 propagators, so degree of divergence is 2 minus d. So we expect that for d greater than 2, this integral should converge, but this does not happen because there is a delta function. So once we use the delta function, that will make the other delta functions linear in Q. So it will increase the degree of divergence. So the actual divergence is actually 0 for this kind of integrals with all Whiteman propagators in d dimension. Okay. And in UV this integral one can evaluate with a cutoff, with a hard cutoff, and it is this, where sigma c is D minus 2-dimensional parallelogram. So it's the volume of a parallelogram. And so we have considered all the momenta Ki are linearly independent, and then we get this kind of result. And this actually diverges for only space like cut momenta. So for other momenta, this integral is 0. This integral actually is 0.
Wait,
So not only that, yeah.
sorry, is this true even if, was it important that it was an open system or just the contours?
Just this integral.
So even if it was not an open system, we were working on this contour, we were going to say that.
Right, yeah. Right. And not only that, this cut momenta, this linearly independent cut momenta, these also, in the linear span of this momenta, there should not be any time-like vector. This is completely space-like. So this cut momenta form a space-like hypersurface. So then only this integrals diverges.
N again, where N is the
N
number
number
of propagators.
of propagators is D minus 1. D minus 1. Right. And these divergences are non-local because there is a momentum factor which come in the denominator. So sigma c is roughly of this form 1 by k to the power d minus 2.
So what you are saying is you take an ordinary quantum field theory, zero temperature, you try
Right.
to compute the Weizmann function.
Right. Then it
This vacuum 5 to the 4th theory, you will find unacceptable divergence.
Right.
You will find strange divergence.
yes,
Why don't we know about this before? Nobody's tried to compute Weizmann coordinates.
maybe this is
Incredible, right?
yeah,
So what is this? This is nothing to do with the openness.
nothing to do with openness.
Non-local divergence is open.
Nothing to do with openness. Maybe in we have not checked. Maybe in closed system, maybe this cancel among different diagrams.
No,
Maybe.
What, so for example,
It can be possible. I mean, because there are many triangle diagrams. Say, for example, triangle diagrams. There are many triangle diagrams, and this kind of divergence may cancel among different diagrams.
theory, let's say,
True.
file square.
Hmm.
You just have these four funny types of propagators,
Hmm.
and then you are constructing this dash,
Hmm.
straight, solid dash, and so on, right?
Yeah.
W.
Hmm.
And now what is it supposed to cancel against?
For example, say this diagram. A simple diagram. And there could be other diagrams. For example, say this. This is not Weizmann propagator, but we can write as a Weizmann propagator because a Feynman propagator can be written as two Weizmann propagators minus the anti-time order propagator. So we can write it that way.
See, isn't it true that in at least a closed system, every correlation function is an appropriate analytic continuation of the Euclidean correlator?
Yes. Yes.
Therefore, if the Euclidean correlator doesn't have any strange divergence, then
Right.
at least in the closed system, isn't this more or less a theorem that all correlation functions have to be as well defined as you? I
Right.
put the counter term that makes the Euclidean correlator finite, everything will be fine.
Yeah. Yeah.
So it's almost like what you're saying has to be a theorem. That in the closed system it has to cancel.
In closed system has to cancel. Yes.
You agree?
Yes.
Okay. Now suppose I make an open system by integrating out one more massive field. This is then a closed system. So even there it has to cancel.
Let me make a point. Sorry. Yeah. I think this kind of diagram won't appear in closed system because you won't get this kind of vertex. You won't get this kind of vertex in closed system where one dotted, one solid. This kind of vertex don't appear in closed system.
Wait, I'm missing all the details, but
Yeah.
do you get any diagram that has unacceptable divergences in closed systems?
No.
No.
So this here did not have any legs, right? This is just a loop by itself, or does it have some legs sticking out?
Whatever legs you put, you have this kind of terms.
Where did that vertex come from? The three thing?
Okay, you can make it 4. It doesn't matter. So you have one dotted, one solid. So that only appear in closed system.
Because odd angle. Sort of,
Yeah. Right.
Okay.
So it's because the mix no
because the
legs-
mixing term.
No, but if there are no legs sticking out, just the loop by itself, then you have this
Actually,
propagator,
that-
right, which is the
Right.
Whiteman propagator.
That diagram
With only
should
one
be zero.
propagators, because in
Because
closed
there is
system.
no, here you're analyzing the thing with no, there are what, there are legs sticking out of this.
No, I'm saying whatever leg you put, this diagram will only come from open system. That's what I'm saying.
That is not cool. I am slightly surprised because
I see, because the vacuum bubble you don't want to talk about at all anyway, because that is zero.
There is
That
no
will
vacuum
just
bubble.
be cancelled.
Yes, huh. Yeah.
Sorry, while Rajiv is formulating his question, let me ask you.
Huh.
So suppose I can make an open system by taking closed system and integrating out a massive field, let's say.
Right. Huh.
So in that UV theory, there are no funny divergences.
Right.
So how did it happen that funny divergences appeared when they couldn't have been there in the beginning?
Yeah.
It can only be some interchange of order of limits or something like that.
Yeah. Might be.
It could be that basically you're taking your effective theory too seriously, right?
Yeah, maybe those are constraints on the effective theory, that's it. Because he's starting from nothing, right? He's just writing down all possible terms.
Yeah.
so the other question is have you looked at that because admittedly we do it in a different language of A and D,
Mhm.
but such terms seem to appear and then there are a set of terms which basically go to zero because there is some identity coming from the fact that your four Green's functions are not independent.
Yeah.
It's just the fact that there is a commutation relation between your
Right.
basic objects, right?
Mhm.
So have you tried to impose that and you still see that in this function?
Yes. Yes. We have imposed that. If somehow these are convergent, then everything is fine. All works. Everything. Other properties work.
I'm sorry to slow you,
Huh.
I just want to confirm once more.
Huh.
If we did this calculation in a nice closed system, we would see no funny divergence.
Right. Yes.
Yes.
Huh.
But in the closed system, as I was saying, there is a vacuum diagram, right? Which is this,
Huh.
which would be divergent. So there one should understand how that is cancelled. You just mentioned a principle that if you set phi L equals phi r,
Mhm.
you get 0,
Mhm.
and that guarantees all the vacuum diagrams cancel. But if you see exactly how this is happening, then this will tell you what is the possible, what it can cancel against, right? Because there you could certainly draw this diagram just with the propagators.
No, I don't understand. This is okay. Oh, you mean some vacuum
I would
divergence?
think if you are going to some thermal limit, you would have less divergences. You are telling me you have more. And usually open quantum systems regulate divergences which usually occur in
Hmm.
standard field theories, right? Because you're basically trying to go to a finite temperature, things get regulated.
This is pure UV. At finite
But
temperature.
by adding those noise terms, you must
Yeah.
have effectively generated some temperature in your system,
Hmm.
right? If you have done that.
What does this mean?
I'm saying if you, okay, so the other way of rephrasing this, if you have dissipative propagators and if you have noisy propagators, okay, at least in terms of cutting off divergences, they play the same role as a thermal propagator. In thermal propagator, these two things have to come with some ratio, but roughly finite temperature, your divergences would be, if you take that theory, put it at finite temperature, would you still get this, you would not get divergences, right?
Okay, we have not done that in the finite
No,
temperature.
I'm just saying phi 4 theory at finite temperature.
No, we have not done that.
Okay. So you normally would, because your temperature would cut off also various things. So why are you getting more? I'm also surprised that you're getting more divergences in an open system than in a closed system.
Then in closed system. Yeah.
Because the usual expectation is that it cures.
We talked to Ashok, and he also said if you if you play with the epsilon, then Feynman the integrals are not well defined. So if you flip epsilon, or if you put some Whiteman-Coulter's, replace Feynman-Coulter, then it's not well defined integral.
I mean, we can get Whiteman correlators from Euclidean thermal correlators by the right analytical technique.
Yeah, right. But here this is not possible because things are going on shell. So pole is exactly on the real axis.
It seems to me that, have you done this? I mean, suppose you take a theory with one light and one field you're integrating out.
Yeah.
You look at these things in that theory,
Should be fine, should not.
Yeah,
and
it
then
should
try
be
to see
fine.
what's going on. That sounds like will help you understand what's going on.
Yeah.
Okay, but please, I'm sorry to interrupt.
Oh, right. Right. So these are divergent and non-local, and this is the observation that all of these. Huh.
I just want to like this diagram.
Hmm.
Can you tell me what the lines are?
This one.
Yeah. What is this cross? Does it mean
Cross
that
are the
things
vertices.
coming out of that?
Cross are the vertices.
So how some things are coming out
Yeah.
of that?
Yes.
That's why K1 goes to K2.
Right. K1 go to
Yeah.
goes to.
So with those diagrams, you could have other diagrams also with those vertices,
Yes. Huh.
and they just
They don't cancel. Okay. So this is an observation that that these integrals are only divergent if all of the cut momenta lie on a space-like surface. This is this Q. Q is the loop momenta, and so we are looking at high energy limit. So only the null cone of the loop momenta contribute to this divergence, because we are looking at high energy domain. Okay. All of this has to be space-like. Even they has to lie on a space-like surface. If some linear combination of this momenta is time-like, then this again 0. This is again 0. This integral is 0. So all of this has to be space-like. So this is one observation. And then let me discuss about non-local divergences in other diagrams. For example, few Whiteman-Coulters and few Feynman propagators. Then again, these are divergent, but the structure of the divergence is a bit complicated.
And once again, the closed system would have no divergence.
Closed system would have no
Can I
divergence.
ask you one question?
Yeah.
If you included all your quadratic terms that you have into your propagators, right?
Yeah.
All the quadratic added pieces which are coming from having added up, would the divergence still remain? That is something that you should be able to that's just a counting argument, right? Does that remain?
No, I think that it will remain, because this is a UV divergence, right? And that will just
No, but you're saying
make
it's a
some
mixed-
cutoff.
You're saying it's a mixed thing.
You're saying it's mixed UVIR, right?
Yeah, mixed UV-IR.
Maybe what you're saying will work.
I think maybe there will be some IR cutoff.
I'm saying it's
Huh.
simply very easy to just take your effective theory and take that effective propagator and it's pretty
Actually, the
simple,
effective propagators are not Whiteman propagators. Actually, effective propagators are not Whiteman propagators,
right?
because okay,
You have an effective action, from that you can construct propagators.
Yeah,
Like
yeah.
the quadratic part of that effective action.
Mhm.
If you use those propagators, does this get cured? Because
Oh.
UVIR mixing would, it can be. That's a question. Because then you would basically say that, I mean, if I'm taking my effective theory seriously, I should need to put that quadratic piece of that effective theory into the propagators that I'm now going to use to calculate added pieces. Right? See, because what happens, the reason I'm saying this is experience from doing other calculations, that once you do this open quantum system business, there are often, if you had derived it from some microscopic theory, okay, various terms that you write down are not quite independent. Various, in fact, quadratic couplings that you write down, you can now use whatever thing to generate this, they get related. Okay? And those relations are often used to cancel divergence. You cancel a bunch of diagrams saying they're zero. Divergent, non-divergent. So that's an experience having done other calculations, right? So it's a question of whether putting in just any arbitrary effective theory, you might have screwed up some of those delicate balances. Which is where Shiraza's thing coming, actually doing it for microscopic theory, you might see some of this going.
You know, I mean, I'm very sorry for slowing you down so much, but you know, in about 15 minutes we'll have to go if we want lunch.
Yeah, yeah. Oh, yeah. Right. Okay. We move on.
What was the diagram before?
Sorry. This is just a general diagram with few Feynman and few Whiteman. And again, it's divergent, and the observation is the cut momenta consists of the which flows along the Whiteman propagators. Those have to be on a null hypersurface. Then only it is divergent, otherwise zero. So this is another observation. Now, non-local divergence in open 5-4 theory. So these are the diagrams which have non-local divergences. All other diagrams can be written as a combination of these three. The divergence structure is this. Okay, let me move on, and I want to talk about this part. This is a holographic approach to open field theory. Yeah, right. So a microscopic derivation is not so easy, but we can derive using holography.
You get the answers, but maybe easy to identify the divergence. Anyway.
But if you take a linear coupling to a quadratic bar, right? Then the effective theory is still quadratic, whatever is coming from the bar. Why will that also have this divergence? Because that's something you can do, right? Because even after integrating out the chi fields, you have a quadratic theory in phi. Now add whatever interactions you have. I'm just simplifying your system bar coupling.
Yeah, we are doing this initially, trying to derive this initially, and then we didn't have this idea that we thought this phi chi squared. That means system field is decaying to two Bath fields. That is the most convenient picture.
The best thing is linear coupling, phi chi.
Yeah,
That will simply let you do everything, integrate out the Bath completely without having any issues.
Right.
And this is the standard thing, you do coupling a harmonic oscillator to a Bath.
So we used this recently proposed holographic Schwinger-Keldysh prescription. The prescription says that that consider ADS D+1 black hole and complexify the radial direction in Eddington-Finkelstein coordinate. It seems that this coordinate is important in this kind of analysis. We don't know yet why this coordinate is relevant. Okay. So if you write this action in this coordinate system and complexify the radial direction, and if you try to solve some field equation, then it has a logarithmic behavior. So that means it has a branch cut. So this is the branch cut which starts from the horizon and extends to infinity. And so this is the proposed contour, that you start at the boundary, conformal boundary, and it comes to the horizon, doesn't touch the horizon, but take a cycle around the horizon and then goes back to the boundary. Okay. So this is the contour, and the prescription is that if you solve for the equation of motion and get the onshell action, if you integrate out the radial direction along this contour, then this boundary end points will be Schwinger-Keldysh degrees of freedom. So that is the prescription. Yeah, that's it. So here this point will represent the left degrees of freedom, and this will represent the right degrees of freedom. Okay. So a better way to visualize is in this picture. Here this black one, the black one is the holographic Schwinger-Keldysh contour, and this circle, this ellipse is the complexified radial direction, and here these two endpoints are the Schwinger-Keldysh degrees of freedom, and here this angle, this wedge, that is the boundary Schwinger-Keldysh contour. Okay. So here this is the Eddy's metric in Eddington coordinate, and we define a new variable chi, which is this chi is nothing but some normalized. It is a normalized tortoise coordinate. And this right, and so we use some normalization. By using that, chi at infinity plus epsilon becomes 0, and infinity minus epsilon it becomes 1 along the holographic Schwinger-Keldysh contour. Then we write the phi4 action in this geometry, right, and we impose these two boundary conditions, that the solution is regular at the horizon, and yeah.
One back, please. Where would you need this chi coordinate? Why can't you just work in terms of R and V?
Just the calculation becomes simpler.
The chi sort of blows up, has a log singularity here.
Yes, yes.
Whereas R and V are just fine, right?
Yes.
So all your physics is coming because you go to the chi coordinate.
Right.
I mean, branch up and so on will be because of the chi.
Yes.
Log in the chi.
Right.
So I want to understand then why you have to use this.
Because all the non-analytic property that is inside chi.
Yes.
So when you write the solution, so you can then identify what are the analytic part and what are the non-analytic part.
Yeah. So you have a solution which in R and V is totally fine.
Yes.
And then your prescription is that you have to go to chi, and I haven't understood it. I mean, the whole point of Finkelstein was that you don't have to go to this chi.
So we don't go explicitly,
Okay.
but we just use this definition.
You use the definition.
Yeah.
I see.
We don't go explicitly.
I see.
Because in the solution of the advanced propagator, so chi appears. So it will be some integral of it will be some integral of d chi dr. So that's why I wrote it this way. Right. So impose these two boundary conditions. Here G plus is the retarded Green's function. That the retarded Green's function should be irregular at the horizon, and at the conformal boundary we choose this normalization that it is 1. So with this we write the solution, which is a linear combination of the retarded Green's function and the advanced Green's function. And then now you see here that there is chi appearing in the advanced Green's function explicitly. So that is the reason. So after that we identify these two degrees of freedom, that at RC plus epsilon at the infinity, that is identified with phi L, and the lower branch phi is identified with the right degrees of freedom in the Schwinger-Keldysh contour. So once we do this identification, then we can write this solution in terms of phi R and phi L, and then we will integrate out the radial direction. And we don't have the full computation yet. We have not done the computation yet, but we have these answers. The computation is not done yet. We get a non-local influence phase, and we in the large temperature limit we can get go to the local limit. So there exists a derivative expansion, and we found linear fluctuation dissipation relation at the quadratic level, and at the quartic level we found a nonlinear fluctuation dissipation relation as well. So previously we found this nonlinear fluctuation dissipation relation in a particle context, but in a field theory also we found the same fluctuation dissipation relation, but even before doing the integral, even before doing the chi integral at the integrand level.
So it's relating what to what?
It's relating phi average, phi difference cube dot and phi difference to the power 4. It's relating these two. It's relating the coefficients between these two.
That's not part of your Lindblad or whatever.
No, that's not part of this. Lindblad is saying just that phi average, all powers of phi average should be 0.
Right.
And that is also satisfied actually. Yeah. Now to comment on non-local divergence, since we have not done this quadratic calculation yet, we can't comment much. But here at the quadratic level, so we are trying to do in a different basis. So we can change basis by taking combination of phi average and phi difference. So in one basis we found non-local divergence, but in this basis, in average difference, we didn't find. So
So you're saying divergence may be cured
yeah, maybe cured.
when you put this relationship?
Yeah. No, I'm sorry. Not putting this relation by going to a different basis.
How can that be?
I don't know. I was actually. It may be. Because there are two limits which we are taking. So one is going to the boundary first, and then changing the basis, or going to a different basis, then take the limit. I don't know. Maybe taking limit is.
Sorry, the issue that you mentioned was independent of its holographic interpretation.
Sorry, what?
The issue, the divergence was had nothing to do with the holographic.
Divergence was nothing to say. Right.
So
Yes.
are you saying that when you do holographically it goes away, or
No. I'm saying that.
two limits you talk about what?
Yeah, I'm saying that if you take a basis, go to a different basis, which say f. Okay, I don't have it actually. Some linear combination of phi average and phi difference. Okay, some coefficient with phi average plus some other coefficient with phi difference, and then integrate over chi. So there is integral from RH to RC.
Sorry, why is this holographic? Can you say this condition for vanishing of the divergence in a way that does not refer to holography?
This does not refer to holography.
What is RH?
RH is the horizon. I'm saying when we are integrating.
In field theory, can you not say that the conditions for vanishing of the divergence is that you would? I'm totally confused.
No, I'm saying okay. Yeah. So to get the boundary Schwinger-Keldysh, we need to integrate over along this contour.
No, but
Integrate the field along this contour.
you are saying perturbatively this does not go away. That's what you are saying.
Which does not go away?
This divergence, even with the basis change, somehow
Right.
holographically it goes away.
Yes. I'm saying that it does not go away in one basis.
Are you getting it? Shiraz?
I'm not getting it either. Is this a divergence in your holographic calculation? Do I understand you're calculating something holographically?
Yeah.
And you're asking whether or not there's a divergence?
Yes. Right.
That holographic calculation has no loops.
No loops.
So it's just a classical calculation holograph.
Right.
One classical calculation gives you a divergence.
Yeah.
Second classical calculation does not. Is this right?
Yeah. Right.
So it's totally different thing.
I see. So these are not your non-local divergences.
No, these are non-local, as in the divergences of this form. So there is a cutoff
So it must be
RC.
a statement about strong coupling. Right?
There is a cutoff RC.
Okay.
So the divergence is of this form. Something like that. Yeah.
Okay.
But just by solving classical differential.
By solving classical differential equation.
Okay. But so you're saying that this prescription has an ambiguity. That's what you're saying, right?
Yeah, I'm saying that. Yes.
This Liu prescription is ambiguous. You do it in one way, you get something. You do it in some other way, you get something. I think it's just some statement about the holographic dictionary.
Yes.
But now how does this now relate to your non-local divergence?
We still don't understand. We still don't understand why doing this in a different basis and then integrate out the radial direction is different from this first integrate out, then
Integrate out means solve some classical differential equation, right?
yes, right.
So does this have to do with the strong coupling curing your perturbative divergence? In one basis, one choice of basis. Is this what it's going on?
I don't understand at all. First, like to understand algebra.
No, but even what is the claim?
I think he's saying that he's not even getting a unique answer at strong. Two
Yeah.
different ways of doing the calculation at strong coupling are giving two different answers. So that's the first confusing thing.
Yeah. Actually, look, when we're doing this for a particle, then also we encountered similar things. Then we thought, actually, then we only did in average difference and found some finite answer. Yeah. Actually, this basis which I'm talking about, this F and the two. This is again some linear combination of average difference. These are actually non-local function, as in there is there is this factor, Bose-Einstein factor, something. Yeah. So 1 plus n times phi a minus n phi difference. This is 1, and phi f is n into phi average minus phi difference. N is the Bose-Einstein factor. This. So doing the calculation in this basis is no. So we're getting non-local divergence. Doing the calculation in this basis. Right. So yeah, these are the observations. Right. And the conclusion is that I get non-local divergence in open QFTs, and we hope that the quartic action will also be local, and we have to do the integration first, to do the calculation first. And yeah, any question?
So this fluctuation dissipation theorem, you can translate it into a statement about correlation functions.
Yes.
So once he's translated the statement about correlation functions, that should be some statement, for instance, some statement about correlation functions in a thermal quantum field theory.
Right.
And that's some unknown statement about correlation functions in a thermal quantum field theory.
It's just no.
Something that people have not yet found out.
People have not found any fluctuation dissipation at the nonlinear level.
Let me not
Yeah.
talk about fluctuation dissipation.
Okay.
You've got some effective coupling here, effective coupling there.
Yeah.
Then you can use that to compute correlators.
Yeah, these are correlators. Yes.
Okay, and your statement is that the two correlators are
Related. Yes.
Now these correlators are all some analytic continuation. Let's work in the case of a thermal field or vacuum. These are all analytic continuations of the same Euclidean
Right.
correlation function in a thermal field theory or some vacuum field theory. Now, either these things are equal or they're not. One should be able to check that. I mean, should follow, presumably, I'm asking, can't you use the usual methods of quantum field theory, to, at least in special cases, to prove this thing? Right?
You maybe
I mean, if it's always true,
yeah, right.
presumably follows from some very general consideration.
Right. Yeah.
Perhaps it's just some statement about some analytic continuation. Because in a way, the thing that's odd about this is the following, right? Suppose you took a Euclidean quantum field theory, you have many fewer couplings than you have here.
Yeah.
Because there aren't two phi's.
Yes.
There's one phi, right?
Mhm.
So all these couplings are somehow
Related. Yeah.
artificial.
Yes.
They're all coming from analytic continuation of same basic data.
Right.
I mean, if you have closed temperature, closed field.
Field theory.
Yeah. Exactly.
Right, so it's not surprising there should be relations between them.
Right.
And should one be able to just work it out systematically?
Right. Right. Because all are coming from.
This holds even when you do have a coupling to some open part. That would then maybe you're saying even with
Finite
that
temperature.
coupling, even
Finite temperature is an example of coupling to a bath.
Yeah.
Even there,
Even there, yeah.
in Euclidean space, it's fewer couplings. What is
Yeah.
not so clear is whether something that is local in Euclidean space will translate to local
Yeah.
in the double quantum. That I suppose is the non-trivial. But it sounds like a real opportunity to be able to just sit down and try to prove this.
Yeah.
Using the usual rules of, since you've identified a very interesting looking phenomenon.
Maybe can be derived from a microscopic theory.
Yeah,
There's that.
you shouldn't have to do more than analytic continuation. Right? Because you've got Euclidean theory.
Yeah.
You know that all these correlation functions follow from analytic continuation of the same Euclidean group.
Yeah.
Just that statement with luck and very little else might be able to give you this.
Yeah.
And maybe I can ask you the same thing along these lines. In the holographic prescription, once again, the holographic prescription should in principle follow from the statement that all correlation functions should be analytic continuations of the Euclidean correlate. Holographically, we know how to compute the Euclidean.
Yeah. Right. Yes.
Okay? So just analytically continuing that should give you this prescription.
Okay. No, but is this clear? Because this relation, these come from non-equilibrium physics, right? But
Well, is finite temperature an example of non-equilibrium?
I mean, it may be, but it could then become somewhat not interesting. The fact that it holds for more general things could be the interesting part, right?
Maybe. But at least either some of
At least
trivial
in that class,
in this class, one should be able to.
But is this always true that that Euclidean correlates contain all information about say non-equilibrium?
Well, if you're interested in Euclidean correlators, if you're interested in non-equilibrium at finite temperature,
At finite temperatures.
maybe it's more difficult when you have rows.
Yeah.
But let's take a special case of finite temperature. Then I thought it was the general wisdom, and maybe you'll correct me, that all correlation functions are analytic continuations of the Euclidean correlate. Is that not true?
Yeah. Okay. That is true. But okay. So for example, at finite temperature there will be this infinite sum. So because there are Matsubara frequencies,
Yes.
so there will be always the correlates will always be infinite sum.
Yes.
So then, I mean, is it practical? Because
Practical is another matter. You see,
okay.
if you've got some general thing, you can often just prove it just with the fact that you're doing an analytical. You don't have to do a calculation,
Okay.
right? So at least, as Abhijit said, maybe what you got is something more general. Though all the evidence so far is for zero temperature and finite temperature.
What is the
Well, I mean, open also, right? Open. This was open system.
Yeah, this is open system.
So you can think of opening the system up at zero temperature and then turning on the temperature also. That's something more than just putting the closed system at finite temperature. No?
Open system and I need to understand this open system. The open system was, this is more than just integrating out another field theory which was also at zero temperature.
No, I think it's that.
Yeah. Okay, so then it was just in the end some zero temperature thing.
No, but now the I mean, for example, these mixed terms were generated. Was was a result of integrating out this path, right? I mean, if you didn't have this, if you didn't have that path, then you would just have this decoupled pieces of the left action and the right action.
Right, but let's look at the whole theory. If the whole theory was at zero
The
temperature,
microscope with the bath.
with the bath.
Yeah.
The whole theory was at zero temperature, and now you take that, look at the Euclidean correlator there, and analytically continue. In the end, this is some statement about a correlation.
Yeah. Right. Correlator involving only, let's say,
Only these guys. Yeah.
Yeah,
Right,
So
yes.
somehow it must follow from that. Yeah. So without even adding this complication of this path separate.
I mean, it seems to me at least that would be the first thing to.
There is possibility of open Euclidean correlator itself having this divergence.
Yeah, I would prefer. Yeah, by open, I will need to understand what I mean by open Euclidean
So you
correlator.
take two systems, couple them, and integrate one of them.
Oh, two systems, couple them, and integrate one of them out. Okay, and right. So, so then in that situation, what I would do is look at the whole theory.
Yeah,
Then
this,
it's not open.
huh.
Okay? Or by open you might mean, I mean, one example of an open system might mean finite temperature. That's what we normally mean by open, right? Completely
Yeah.
heat bath.
Yes, huh.
That also I understand well. If you're doing something else, I need to understand either of these two situations. I think are well.
Yeah, and then look at only correlators which involve this.
Yeah. Yeah, but you know the thing that will be non-trivial is that it may not be that local terms in this double formalism come from purely local information
Yeah.
of the Euclidean theory. But what you probably have identified is one combination of local terms in this guy that comes from local terms. That sounds very interesting.
But the level of correlation function must be, it would mean, or if you just phrase this in terms of constraints of the correlator,
Yeah.
then it shouldn't matter.
It shouldn't matter, but now you want to say that it's that right? Yeah, you're right. It should just be automatic.
Maybe in some perturbation.
Oh, even more in some analytic functions.
Right, because but his constraint is on this term on the Lagrangian, right? So in order to translate that to correlator, to do some perturbations and so on.
Yeah.
So order perturbation makes some statement.
So either you might be able to prove that there are such divergences from local terms in this.
So at the moment we were not talking about divergences. We were just talking about this fluctuation distribution.
Yeah.
Divergence is confused. But here's, you know, there are two parts of this talk. A, there's this divergences which I don't know what to make of. Since he's saying it's not there in the closed system, but it is there in the open system. But the open system is a closed system. You take the bath into account, right? That confuses me. Okay, but then there is apart from the divergences, there's this part of the talk that sounds very interesting to me, which is the fluctuation distribution. The numerous argument about quantum field theory. That sounds very interesting to me, and it seems to me that you might be able to just prove. An issue completely unrelated. But can I ask once more again?
Yeah.
Just let me ask about the holographic thing. Hong and company have this prescription. Now, since if the prescription is correct, it must agree with what you get by taking thermal correlators and analytically continuing them.
Yes. Huh.
So can one check that this prescription gives the same as what you get from taking thermal correlators and is this obvious or not?
So, someone has to do it.
It was not part of their paper.
No.
Okay.
They don't do it. Yeah.
So that would be a nice exercise in itself, right? Taking the thermal correlator, analytically continuing that,
Yeah.
and showing the leads.